Hello guys, let's solve another LeetCode problem, maximum depth of binary tree. We are solving blind 75 LeetCode questions and we are starting the tree sections. And this is the first problem, so we'll talk about a little bit introductory discussion about trees. And we are solving the first problem in the section maximum depth of a binary tree. This is a LeetCode easy problem. So if you just use the recursive solution, it's pretty easy to implement. But to make it efficient, we need to think about how we can use less storage. So let's talk about tree first. So for the case of binary tree, there are two things you need to consider. Actually, a root node. And for each of the node, it can have left child and right child, right? So if this is a node n, so there will be a left pointer and right pointer, L and R. So this is the basic introduction of tree, a binary tree. And you can take a look at the tree node part in the code. So you can see the class tree node has three things. One is actually self.value, which is represent the value of the node. So for the case of if our first node is 3, so in this case, this node value is 3, right? And then the left node is 9 and the right node is 20. So the value actually points to the integer value of 3 and the left pointer represents a tree node again. And the right pointer also points at tree node again. So to solve this problem, we want to find out the maximum depth, and maximum depth for this one, if you take a look at the examples. So maximum depth is 3, and the maximum depth is defined number of nodes along the longest path from the root node down to the farthest leaf node. So if you start with root node 3, and if you go to the farthest leaf node, so you can go to 1, 2, and 3. So you basically go to 3, 20, and 7, and 7 is the farthest node. And you want to return basically 3 because you have 3 nodes, root node, the right node, and also this 7 node. So if you know the recursive solution, it's pretty easy to implement. Basically for each of the level, what we are trying to do that if there is not a null pointer for each of the node, we can basically go to each level down. And for example, if you take a look at the 3 here, right? So let's draw this one here. So we have 3 and then 9 here, right? And then it has 20. And 20 has 2 more nodes like 15 and also 7, right? And now let's talk about if you have only one node. So if you have only 3, we want to return just 1, right? And for 9 and 20, if you have 2 nodes, so both there is 2 nodes. So basically your depth will be 2. And when you go to the next node, like 3, so this is the 3, right? So if you want to write a recursive solution, basically, if there is a root node, valid root node without null pointer, you return 1. If you go to one level down from left and right, you basically want to return that node plus 1 because there's a 1 level down. And from 20, you go 1 level down and then you return 1 plus left node. So if you just want to use the recursive solution, it's not that much tough. If not root, you basically return 0. And then to make it clear, you can calculate the left side. So the left side is self dot max depth. And you basically call root dot left. And for right side, same as like self dot max depth root dot right. So you basically get the two values from left node and right node. And when you are returning, you should be one level up of L and R, right? So that's pretty much the recursive solution. So let's go ahead and submit this guy. And you will see this is one way to use the recursive solution to solve this problem, right? So let's talk about the runtime. We are going through each level one at a time. So you are basically traveling all the nodes. So order in runtime, you need order in runtime. And for the space complexity, you are not explicitly storing any value, but in the worst case, there will be n steps on the recursion stack, right? So it can be order of n, right? So that's the recursive way. But if you are asked to implement it is the iterative way, let's talk about how we can implement this one using iterative way, right? So if you want to do it in iterative way, you want to solve the same problem, but you need to use some sort of data structure. You can use list, but list is pretty inefficient. So we will go through the BFS structure, breadth first search, where we will travel this level first and go to the second level. So this segment, and then we will again go to the third level, right? One level down. So you can use Python collections libraries to use deque. So I will use a deque. And for the initial case, we'll just append this root node. And we will also append another null node. And I'll explain why this is necessary. And we'll keep track of the level. So we'll start with the 0 first, right? And while you have your deque, you basically pop the value deque.pop left. If not n, if it's not a null pointer, then you basically update the level by 1. If not a deque, you are end of this list, you just basically get out of it. And otherwise, you add one null pointer and you continue. And if it's not null, then if you have a left pointer, then you basically append that node to the queue. Same as if you have a right pointer, you just append this right node. And finally, when you are outside of this one, then you can return this level. So this is the way how you can implement BFS algorithm. So something like graph search algorithm, like BFS, how you traverse level by level. For the tree, how we are doing, we are using a queue structure, right? So, and for Python, we are using deque. You can use list, but the main problem is then when you use list, when you want to do the pop left, it will be order n. But if you use deque, then you can do it actually order one time on an average case, right? Two things to keep in mind when you are doing BFS. At first, you push this root node, and then you basically pop one node at a time. And if there is a left pointer or right pointer, you basically again push those things into the queue, right? That's how you go through this whole BFS. So if I want to explain it, so at first, if you have this queue, whole queue, at first you push this 3, and then you pop this 3 and push the second two element 9 and 20, right? Here. And again, you actually push this and pop this 9 and push the left and right pointer. It doesn't have any, so it will not do anything. When you pop 20, you have 15 and 7, right? So you again actually push those things. That's how you traverse the whole tree. But if you want to go through level by level, what we actually pushed after the root, we pushed a null node here. So I'll just make it a this one. After 3, we actually put a null node here, right? And then when we reach this null node, we know that actually we covered one level down. So that's our sentinel character, right? So then for 9 and 20, we again, we push another none here, right? And also none here. And what we are doing, when we are popping left, we are checking actually, we are getting this null node. Each null node actually represents your end of this level. So we are increasing the level by 1 and finally return this level, right? So let's check this one and then also submit this one. Okay, so that's the iterative way to implement this problem. So let's talk about the runtime complexity for this one. So you are basically inserting all the node only once, and also you are putting the level of none. The space complexity would be order of n, right? So because in the queue we'll have at most n plus level number of nodes. So it will not be more than 2n nodes. And going through the node one at a time. So you're basically also the runtime complexity also order n. So that's the iterative way of implementing this algorithm. It's an easy problem, but it will give you some sort of background how to solve the next tree problem later section of this LeetCode. That's pretty much it for this problem. Thanks for watching. I will see you another LeetCode tree problem solution video.